In this video, we are not recommending a specific chilled water control strategy. Instead, we will examine what happens inside a chilled water system when different design and control decisions are applied. All scenarios use the same cooling load. What changes is how the system responds. Baseline conditions. Why load is constant. In these examples, the cooling load is held constant at 500 tons, so we can clearly isolate cause and effect. In actual operation, the chiller does not know the building load in tons. It only responds to control signals, such as chilled water supply temperature, return temperature, coil valve position, air temperature stability, and zone demand. When those signals indicate unused capacity, the control system allows temperature or flow set points to change. Scenario 1. Resetting chilled water supply temperature. Step 1. Starting point. Traditional design condition. At this condition, the system delivers 500 tons using a 10-degree temperature difference. Approximately 1,200 gallons per minute are required to move that heat. Step 2. Why the supply temperature is reset upward. From the control system's perspective, cooling capacity appears to be available. Valves are not near wide open. Zone temperatures are stable, and supply air targets are being met. Based on these signals, not a known tonnage, the system allows the chilled water supply temperature to reset upward. Step 3. Coil valve response. As the supply water becomes warmer, each gallon carries less cooling capacity. The control valves respond by opening further to maintain the same cooling output. This is a normal and expected response. Step 4. Flow increases. With a smaller temperature difference across the coil, more water is required to move the same heat. System flow increases accordingly. Step 5. Pump and chiller impact. Pump energy increases due to higher flow. At the same time, the chiller sees warmer entering water, which reduces lift and can improve compressor efficiency. Energy is not eliminated. It is redistributed within the system. Key observation. Resetting chilled water temperature preserves capacity by increasing flow. The system trades pumping energy for reduced compressor lift. Scenario 2. Designing for a 15-degree delta T. Step 1. High delta TT design condition. In this scenario, the coils are designed to operate with a larger temperature difference. The same 500 tons are delivered using significantly less water. Step 2. Why flow is lower. This is not a control adjustment, it is a design decision. Each gallon of water removes more heat, reducing the flow required to meet the load. Step 3. Pump impact. Lower flow directly reduces pump energy. This is one of the primary motivations for higher DT designs. Step 4. Chiller impact. The chiller sees warmer return water and lower evaporator flow. Capacity is still met, but through fewer gallons rather than colder water. Key observation. Designing for higher DT shifts. System performance toward lower flow and reduced pumping energy. Up to this point, we've examined two distinct scenarios using the same cooling load. Rather than introducing additional strategies, we'll now pause and summarize what these examples reveal about chilled water system behavior. Fixed cooling load. In all examples, the cooling load remains fixed at 500 tons. This allows us to isolate how temperature difference and water flow interact, without changing the amount of cooling required. Core relationship number 1. At a fixed load, DT determines required GPM. When the cooling load is fixed, the temperature difference across the system determines how much water must flow to move that heat. With a 10-degree temperature difference, approximately 1,200 gallons per minute are required. Increasing the temperature difference to 15 degrees reduces required flow to about 800 gallons per minute. The load did not change, only how the heat was transported. What this means physically. A higher DT means each gallon of water carries more heat. Fewer gallons are needed to move the same cooling load. Core relationship number 2. At a fixed load, changing flow forces DT to change. The inverse is also true. If water flow changes while the load remains constant, the temperature difference must adjust to compensate. If flow increases while the load stays the same, the temperature difference must decrease. If flow decreases, the temperature difference must increase. This relationship is automatic and unavoidable. The system will always balance flow and temperature difference to satisfy the load. Energy implications. Pump energy perspective. Increasing flow increases pump energy, often significantly. Reducing flow lowers pump energy, sometimes dramatically. Chiller perspective. Changes in DT and supply temperature influence chiller operating conditions, including lift and efficiency. The impact depends on how the system is controlled and how far variables are allowed to move. With the same cooling load, increasing DT reduces required flow. When flow is adjusted, temperature difference responds automatically. These two variables are inseparable at a fixed load. Final recap. In a chilled water system, load, flow, and temperature difference are linked. If the load is fixed, changing one forces the others to respond. These examples do not prescribe a strategy. They illustrate how the system behaves, so the implications of any control or design decision are easier to understand. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.